it's under the window, and there is more bokashi on the table. Yeah. Yeah, but put it high enough so we don't. Can you take apart the metal rack from the laminar flow hood and pull it out, because it kind of stays in the way?
Yeah, it's. I'll take care of it.
Yes, there's a metal rack in the back.
I understand, but it's elevated high enough. It clears that lower tray.
So okay, all right, okay. But eventually, because of the combination between my passion for combining organic chemistry with biology, and because there is a limited amount of students that need invertebrate zoology relative to the students who need microbiology, and the diversity of microbiology, I ended up saying microbiology is a more interesting thing to teach. Okay, because you teach biotechnologies, you teach infectious diseases, you teach about the diversity of microbes in geochemical setups, how do they interact and form soil, for example, and also there's so many other things to say.
Okay.
So I ended up with this, and then the act of teaching, I just like teaching. Okay, I like doing research a lot, but I also like teaching. To me, over time, it becomes, like I said, an acquired taste, and then after a while you start liking it.
Okay. Would you please explain the current research your laboratory team and your collaborators are working on?
I do a couple of projects on interaction of microbes with minerals. Some of the projects I do are with minerals from rocks.
Okay.
That allow the microbes to extract energy from the rocks. We do a lot of work with NASA on a project with meteorites, and we actually have a grant to run the rover this summer on Mars. Yeah.
Would you mind elaborating on that?
My collaborator Martin Fisk from Oregon State University, we wrote a grant, and he's the PI of the grant. And this summer, a mission called, it's a rover, I think it's called Opportunity. I have to look into that thing, MSDL. This rover, Mars Science Laboratory, lands on Mars in August. So Martin is getting trained right now, my collaborator.
Martin
Fisk.
Fisk, okay.
Yes. He's getting trained by NASA at Jet Propulsion Laboratory in Pasadena to ride the rover on Mars. So he stays
Oh my goodness.
How cool is that?
And
I'm a co-PI, I'm a collaborator in that grant.
Wow.
He's the PI, I'm the co-PI. And the way, it's indeed exciting, because this is a big opportunity, and if we get lucky and the rover does land, because this is a 50% chance of it may be broken. If we get lucky, then for about at least 1 year, we are going to ride the rover. How cool is that? So
wow,
say,
this is the biggest grant I've ever heard.
Yeah, go there, take a piece of rock. So what we do, this is one of the research I'm doing this summer. What we do is we are testing instruments that are equivalent to the ones that are on the rover already. We load them, we take pieces of rock, like that rock at the window. We polish the rock, because the rover has a unit that is called RAT, R-A-T, comes from a rock abrasion tool. So it ablazes if you like a sander. It creates a smooth surface, and then puts a magnifying glass with a laser beam and tries to look at the composition of the chemicals that are present on the surface. And we have discovered last year that there are some microbes in a cave in Oregon that have a physiology that may be present on Mars based on physical properties they have. So now we are taking those microbes, which we grow. Okay, let's just grow the microbes, Okay. We take those microbes. And we load them up on pieces of rock that resemble the Mars rocks. How do you want to understand?
Yeah. Sometimes it gets stuck.
Yeah.
I think it was one of the
Yeah.
most exciting questions I was going
Yeah.
to ask you about.
So, go ahead.
It was supposed to be. My question was about the olivine.
Olivine. Yeah.
Okay,
This
my
is
question.
the Olivine project.
I was so excited
Yeah,
about this.
yeah.
I was going to ask you.
Okay, so-
one of your most exciting researches about this special mineral is
Yeah.
olivine, which comes from volcanic rocks. Can you explain in detail the special discovery that led you to?
Okay. So there is these caves in Oregon that have ice, and they are similar to lava tubes on Mars. Which
But
are,
this is different from
it is the same,
Mars.
it's the same project.
Oh, it's the same
It's
project.
This is the same project. So it looks like this. There is this.
Seriously, it looks like this.
This is peridot. This is pieces of crystals that are coming from a rock that looks
my
like
goodness.
this, and they mine them. Okay, so you have a rock like this. This is rocks
Yes.
like similar to Mars.
Okay, and
But
this is where it
sometimes,
comes from.
yeah, sometimes in this rock, crystals are very large, and when you exploit them, you exploit what is called peridot. This is what olivine is. So when you collect it as a gem, we call it a peridot, and you make a necklace of it. Okay. Now we found that there is microbes on Earth that live in those caves in Oregon.
Oregon.
Yeah, Oregon caves, Oregon ice caves. And we found that there is microbes on Earth that live in Oregon, eating this mineral from basalt. And they have a physiology that will allow them to exist on Mars in a recent past. So if Mars was warmer a little bit, because right now Mars is extremely cold. They're talking minus 70 Celsius. Everything is frozen solid, like in a freezer. But in the past, Mars was a little bit warmer.
Yeah.
So when that happened, then this microbe that exists now on Earth, on olivine, in the caves in Oregon, could have very easily grow on Mars. So which means that continuously Mars and Earth have exchanges of meteorites. So which means that whenever Mars becomes more accommodating for life, then on occasion one rock from Earth that lands on Mars reseeds Mars. And so you start having life. Okay? So it goes through an episode, a historical episode, I don't know, 100 million years, and then it disappears. And then again it becomes a frozen planet. And then again it warms up. So in the history of Mars there were episodes where this type of microbe that we find in caves in Oregon could have existed on Mars. So that's what we're looking for. We're looking for evidence that in the past, on rocks on Mars, there were microbes eating on those rocks, and they left signatures, fingerprints. So that's what all those Mars missions are all about.
Wow.
So we're looking for
Can I
organic.
see that?
Yeah. This is This
So-
is peridot. You buy it from the store.
This is just what
It's a
the
gem.
microbe feeds on that
Yes.
you're looking for.
Exactly.
And how is it that you discovered that it actually is there? Is it because of the
We're
meteorites?
looking for it.
Okay.
This is an old research that we do. This is about 10-year-old research. We
Okay.
knew that in olivine crystals, as you look at them in the microscope, there is features. They look like channels, like microtubes, that could not have been produced by biological processes. They must have been produced by biological processes. So for many years, we were looking for microbes capable of doing that. And we found them last year, and we have reported that in an astrobiology paper. Now this year, the story goes like this. Now we take this microbe, the same microbe that it's eating olivine, and we load it up on rocks and olivine. And now we take the instruments that are present on the MSL, the Mars Science Laboratory, and we are going to look at those things to verify at what density can we detect them. And then after the lander lands, we are going to actually go with the rover to a rock and say, do you find anything that remotely resembles the data that you produce artificially in the lab? Because in the lab, you can load the crystal with as many microbes you like. On Mars, you see a measurement, but you do not know if it is relevant or not.
Yeah.
So what we do is this summer, that just makes it exciting, what we do is we take crystals, we load them up with microbes. We use instruments that use the same calibration, types of wavelength, infrared, ultraviolet, and all that thing. We illuminate the rock, we read the fluorescence, we make the observations, and now when the rover starts measuring on Mars, we can calibrate the measurements. We can say, is that measurement relevant to consistent with the belief that there may be some life on Mars or not? The present mission is not a mission to search for life. It's a mission to search for evidence that life may have existed in the past, that water may have existed, that organics may have existed, that sort of thing. We don't have yet a mission that goes to Mars to find life.
Okay.
We're not yet there.
Was there was something about 3 billion years old rock?
ALH, yeah. So it goes like this. For you to get access to such a level of science, you have to demonstrate precedence. You have to demonstrate that you know something already. You know how to do it. And the way we did it is, on Earth, at this very moment, there is about 25, maybe 30 pieces of rock that came from Mars, meteorites. So they analyzed those rocks, and they know those meteorites came from Mars. Okay? So now, we took 10 of those about 3 years ago. We took 10 of those samples, samples of those meteorites. We cannot have the entire meteorite in Portland, but they give you a tiny chunk. We took 10 of those, and we analyzed the olivine crystals in those. And in one of them, we found the same channels, microtubes, that resemble, I know, it makes your goosebumps.
Yeah.
In one of them, we find microchannels that resemble the microchannels that the microbes are making on Earth. Now, we know that meteorite could not have get those microchannels on Earth because that's Nakla. That meteorite fell on Earth in the desert in Egypt. Nakla.
This one
piece of rock.
The rock that you brought to your lab.
Yes, yeah.
Okay, and was it the only rock you took? 10 samples from this specific rock?
No, we took 10 different meteorites.
10 different meteorites?
Because we do not know which meteorite is going to be the one that has those things. So we took samples, one sample from one meteorite, one sample from another meteorite, one sample from another meteorite.
So this was just unexpected discovery?
Yeah, we were looking
for... You were just looking
we're just screening for meteorites.
And you found something?
Yeah.
Oh my goodness.
Okay, so we took those meteorites, we analyzed, and we got lucky that in this one meteorite, we found those channels. So now we go back to Mars and say, okay, now I know how to find the channel. Bring me a sample from Mars. In the future, there is going to be something called a sample return mission. A sample return mission is when you send a rocket to Mars, takes a sample and brings it back to Earth. But the problem is, which rock do you pick? Because you can land on Earth, take a rock and take it back to an alien planet, and if they take a wrong rock, there is no life on Earth.
How is this going to be possible?
What we do is we're looking at what properties